All right, today we're going to take a journey deep inside our own bodies. We're here to understand something we do every single second without even thinking about it, just moving. But as you're about to see, what's happening under the hood, it is anything but simple. Let's get into it.
I mean, it seems totally effortless, right? But behind that one tiny little action is a perfect symphony of electrical signals, chemical reactions, and incredible mechanical forces. So today, we're pulling back the curtain to show you exactly how that symphony plays out. Now, to really get how we move, we first have to agree on what movement even means. Yeah, it sounds super basic, I know. But in biology, motion is literally the signature of being alive. The thing is, not all motion is created equal.
So what's the key difference here? Well, think of it like this. Movement is any change in the position of a body part. Blinking your eyes, shrugging your shoulders, you name it. But locomotion, that's movement that actually gets you from point A to point B. It's the difference between tapping your foot and, well, using that foot to walk across the room. It's a simple distinction, but it's absolutely crucial for understanding the biology at play. Now, what's really fascinating is that life has evolved all these different ways to create motion, from the tiniest microscopic level all the way up to a full-on sprint. So let's take a look at the tiny engines that power the whole shebang.
Okay, so way down at the cellular level, you've got ciliary movement. These are tiny little hairs beating together, and their big job in us is to clear mucus out of our lungs. Then there's flagellar movement. You've seen it. It's that whip-like tail that powers a sperm cell. But the absolute star of our show, the engine behind every single time you walk, talk, or lift anything, is muscular movement. And that's what we're diving into right now. We are officially heading into the engine room. This is the microscopic world where the real magic of motion actually happens. Think about it. You decide to pick up your coffee cup. In a flash, a signal goes from your brain to your bicep. But what happens in that split second inside the muscle itself that makes it tighten up and lift? It's time to meet the main characters in this microscopic drama. Two proteins named actin and myosin. Just think of them as these tiny ropes and motors that are packed inside every single one of your muscle fibers. They are, at the end of the day, the reason you can move at all. And this is how they work together, in something brilliantly called the sliding filament theory. First, that nerve signal arrives. Bam! That triggers a release of calcium. Now, this calcium acts like a key, unlocking the actin and allowing the myosin heads to grab on. Then, using cellular fuel, ATP, the myosin heads pull. I want you to imagine thousands of tiny molecular rowers all pulling on ropes, all at the same time. The ropes don't actually get shorter, they just slide past each other. This incredible collective pull shortens the entire muscle fiber and, boom, that's a muscle contraction. But of course, all those amazing muscle engines would be totally useless without something to pull against, right? They need a frame, a chassis to anchor to. And that brings us to the body's incredible framework, the skeletal system. You know, your skeleton is so much more than just a scaffold. Yeah, it provides support and protects your organs, obviously, but it's also a dynamic factory, constantly producing your blood cells. And it's a storage vault for crucial minerals, like calcium. Yep, the exact same calcium that we just saw as the key to unlocking muscle contraction. It's the essential, silent partner to your entire muscular system. And the engineering marvels that connect this rigid framework and allow it to become this dynamic, moving machine, those are the joints. They are the hinges, the pivots, and the sockets that turn a static structure into pure motion. And these joints come in three main flavors. First, you've got fibrous joints, like the ones in your skull. They are totally immovable. They're fused together for maximum strength. Then you have cartilaginous joints, like the discs between your vertebrae, which allow for just a little bit of give. But the real MVPs of motion are the synovial joints, your knee, your shoulder, your hip. These guys are filled with lubricating fluid, which is what allows for the incredible range of motion we rely on every single day. So, understanding this beautiful, complex system is one thing, but it's also really important to understand what happens when parts of it start to break down. And why this matters is because this stuff affects the health and quality of life for millions and millions of people. Okay, let's start with a problem at the signaling level, myasthenia gravis. This is a really tricky autoimmune disorder where the body's own defense system starts attacking the connection points between nerves and muscles.
So that go signal from the brain, it just never properly arrives, and that leads to this profound and frustrating weakness.
Hey, remember how calcium was the key that unlocked muscle contraction? Well, tetany is what happens when you don't have enough of that key. Without the right calcium levels, muscles just can't regulate themselves, and they start to fire uncontrollably. And that leads to really painful involuntary spasms.
Now, with muscular dystrophy, the problem isn't the signal or the calcium, it's the actual muscle fibers themselves. This is a group of genetic diseases that tragically cause the muscles to progressively weaken and just waste away over a person's lifetime. Now we move from the muscles to the framework's connection points, the joints. Arthritis is an incredibly widespread condition where these crucial hinges become inflamed. And that inflammation causes pain and stiffness, turning that smooth, easy motion we all rely on into a really difficult and painful process. With osteoporosis, the problem lies in the very structure of the framework itself. The bones actually start to lose their density and mass, becoming porous, weak, and dangerously easy to fracture from even just a minor fault. And finally, gout, another really painful joint issue. With this one, sharp needle-like crystals of uric acid build up inside a joint, causing these sudden, severe episodes of inflammatory pain. You know, each of these disorders just goes to show how a failure in one tiny part of the system can compromise the whole machine.
So here's the bottom line. From the whip-like tail of a single cell to the microscopic rowing of actin and myosin, all the way to the complex mechanics of bones and joints working in perfect harmony, your ability to move is an absolute masterpiece of biological engineering. So every step you take, every simple gesture you make, is a testament to this incredible system. We've seen how it works, and we've seen how it can fail. The only question left is, knowing the magnificent and complex machine that you're in charge of, how are you going to choose to maintain it?